Alright, greetings everyone. Today I'll be walking you through the input and output system architecture, the part of the computer system that enables communication between the CPU, the memory, and the vast world of external devices. Okay, so think of it like the nervous system of the computer, ensuring that data flows smoothly and efficiently between the components, right? So we are going to look at an overview of the components, the transfer modes, and then the addressing of the input output system architecture. Right. So without wasting much time, let's delve into it. So before we even begin talking about the key components of the input output system architecture, what is the input output system architecture? So the input output system architecture refers to the framework that allows a computer to interact with external devices like the keyboards, displays, hard drives, and network cards. So it manages how data flows between the CPU, the memory, and peripherals, ensuring that communication is efficient, reliable, and timely. Right. So imagine a very busy airport. The CPU is the control tower, the memory is the cargo area, and the input output devices are the airplanes, right? So the input output system is everything that ensures that the aircraft get to and from the gates without any collisions. That's the runways, the gate, and the air traffic control protocols. Right, so the key components of the input output system architecture includes the input output devices such as the keyboards, the mice, the printers, and more, right? So each of them has their own unique characteristics. And then we have the input output bus, which connects the CPU, the memory, and the devices, just like the runways in the airport, right? So examples include the address bus, the data bus, and then the control bus. All right. Uh, then next we have the input output controller, which acts as a translator between devices and the CPU. And then we have the device drivers. So the device drivers is a software that allows the operating system to talk to the hardware. Also, we have the input output ports or registers, which interfaces for communication, like sending commands or checking the device status, right? And then we have the interrupt mechanisms, where devices can signal the CPU when they need attention, just like the way a pilot will call the tower. And then we have the direct memory address controller, which transfers large volumes of data without involving the CPU much, right? That's improving the performance. All right. So the input output system plays four main roles, right? So the first rule is the efficiency, where it helps bridges the speed gap between the fast CPU and the slow devices using techniques like buffering, interrupts, and direct memory access. Another rule is the flexibility, where it supports all kinds of devices. Okay, so whether the device is fast, whether it is slow, whether it's an analog device, or whether it is a digital device. Another role it plays is reliability, where it includes error detection and recovery mechanism. And finally, another role it plays is the scalability, where it supports uh, easy addition of new devices. So without it, the CPU would have to micromanage every interaction, which you can imagine the chaos and the inefficiency it will lead to, right? So moving on, let's look at the transfer modes of the input and output system architecture. So there are four main ways data can be transferred between the input output devices and the system. And the first one is the programmed I/O. We have the interrupt driven I/O. We have the direct memory access, and then we have the channel I/O. Right. So each offers different trade-offs in terms of CPU involvement, efficiency, and complexity, right? So without wasting much time, let's delve into each of them and let's look at what they mean. So the first on the list is the programmed I/O. So in programmed I/O, the CPU is in complete control. It sends a command, checks if the device is ready, transfers data, and then repeats the process over again. Now think of it like a chef. So we are going to use the analogy of a chef cooking, right? So think of it like a chef personally fetching every ingredient, right? So you check their readiness and then place them in a pot, right? So it is very simple but very CPU intensive, since in our chef analogy is the chef who has to do everything. Okay, so he has to fetch every ingredient that he needs. He has to check the readiness of the ingredients, and also he has to place them in the pot by himself, right? So I mean, the process is very simple, but it is very CPU intensive. Now, an advantage of this is that it is easy to implement, right? But then a disadvantage is that it is inefficient for large data transfers. Actually, it is very suitable for low speed devices like the keyboard. All right. Then we have the interrupt driven input output, which improves on the programmed IO by allowing the CPU to do other work while a device prepares data, right? So this device sends an interrupt when it is ready. So going back to our chef analogy, just think of the chef starting a sous chef on ingredient preparation, right? And only returning when called. Now it's more efficient and still requires the CPU for each piece of data. So it is common for medium speed devices like a mouse or a serial port. Then our next transfer mode is the direct memory access. So DMA takes efficiency a step further. A special controller handles data transfers directly between devices and memory without the CPU being involved after initialization. So going back to our chef analogy, imagine hiring a delivery service to transport all your ingredients at once. Now it is much faster and allows the chef to focus on cooking. So it is ideal for large transfers like reading a big file from a disk or receiving data from a network. And then finally, we look at the channel input output. So the channel input output is used mainly in large scale systems like the mainframes. Now a separate IO processor executes full programs that manage multiple devices. So this one is more like a team of cooks which are handling entire meal preparations with detailed instructions and only notifying the head chef when everything is done. So it is very powerful, right? But then it is expensive and complex. So it is rare outside of specialized systems. Now let's look at how the CPU accesses device registers, right? So we have two ways, and they are the input output mapped input output and the memory mapped input output. So in short, we call it the IO mapped IO and memory mapped IO. So the IO mapped IO uses a separate address space and special instructions, whilst the memory mapped IO integrates device registers into the memory space using standard instructions. So each of them has its own advantages and disadvantages depending on the architecture and the use case. Right. So let's delve into each of them. So IO mapped IO separates device communication from memory. Right. So the CPU uses special instructions like the in and out instructions. So think of it like a separate phone line for calling devices. There's a clean separation, but I mean it needs a specific command. So it's more common in older systems like the x86 PCs. And then the memory mapped IO. So the memory mapped IO treats device registers as regular memory addresses, right? So the CPU uses standard instructions like the load instruction and the store instruction. So it's like using the same mailing system for devices and memory. Right? It's simpler for programmers and more flexible, especially in modern systems like the ARM and USB systems. Right, so here is a side-by-side comparison. So the IO mapped IO has separate address space and requires special instructions, but the memory mapped IO shares address space and uses normal memory commands. So today the memory mapped IO is more common due to its portability and ease of use. Alright, so let's apply what we've learned. So assuming a laptop downloading a large file over Wi-Fi, right? So the devices involved here are the Wi-Fi card and then SSD. We have the PCIe bus, and the transfer is done using the direct memory access, right? And then the addressing is likely memory map. Now, what happens during the interrupt? The Wi-Fi signals when the data arrives, and then the SSD notifies when the write is complete. Right, so the result is a smooth download with minimal CPU overhead. Right, so to wrap up, the input output system architecture is essential for managing communication between the CPU, the memory, and the peripherals. So its components and transfer modes ensure efficiency, reliability, and scalability. Now, direct memory access and memory mapped IO are dominant in modern systems due to their performance benefits. So, understanding input output systems is key to grasping how computers interact with the real world. Thank you.